Namaste everyone, welcome to the class. Now in the last lecture you have seen conditional probability and we have solved few problems based on conditional probability. Now here in this lecture we are going to see multiplication theorem and independent events. So let us first revise what we have done in the previous class. Probability of E by F. Probability of E by F means probability of E when F is known is equals to probability of E intersection F whole divided by probability of F. Okay. So what is this probability of E by F? It is conditional probability. When event F is known, then what is the possibility of event E is given by this formula. How this formula came? Everything we have seen previously. Now, if I rearrange this formula, I will get probability of E intersection F is equals to probability of F into probability of E by F. Now here when I rearranged, I get formula that probability of event E and F together, that means probability of happening both the events together is equals to probability of F into probability of E provided F is known or F is happened. In the same way, we can also prove that probability of E intersection F is equals to probability of E into probability of F by E. Now, you must note here that when I write probability of F into, then my conditional probability will be of probability of event E given F. So when I have written F, then in the second part it is known that F already occurred. And when I write probability of E, then in that case event E have already occurred, that I know. Then probability of happening of E and F. Now this can be generalized. This can be generalized. Here this PE intersection F can also be written as PEF. So when I write PEF, it means I am talking about P of probability of E intersection F. EF, that is probability of both E and F, happening of both E and F, is equals to probability of E into probability of F by E. This is our multiplication theorem. Now if I generalize it for more than 2 events, say for 3 events E, F and G, so probability of E, F, G, this is going to be equal to probability of E, say. So my first event happened, say event E was first, event E happened, then possibility of event F given that E already happened into probability of G given that E and F both happened. So in this way I can generalize this concept. This is our conditional, this is our multiplication theorem. So multiplication theorem is not too different from conditional probability. And there is one more concept, that is independent event. Now two events E and F are said to be independent if possibility of E intersection F is equals to possibility of E into possibility of F. Then we say that the events are independent. Now we have discussed in the previous that probability of P E intersection F is possibility of E into possibility of F by E. Just now we have discussed this thing. Now in case of independent event, we are saying that this is equals to probability of E into probability of F. So from this, what you can conclude that probability of F by E is same as possibility of F. So when your possibility of F by E is same as possibility of F, you will say that E and F are independent. Or when you have possibility of E by F is same as possibility of E, you will say that they are independent. So either I use this statement to indicate the events are independent, or I use these statements. Now here possibility of F provided E happened is the same as possibility of F. That means there is no effect on the possibility of F when I know event E has already occurred or not. So that means E and F are independent. Now we will understand them in a better way when we solve exercise. So let us directly jump to exercise. So here our exercise 13.2. The first problem is probability of A is 3 by 5 and probability of B is 1 by 5. We have to find probability of A intersection B if A and B are independent. So first question, simple, only formula you have to apply. P of A is 3 by 5 and P of B is 1 by 5. So P of A is 3 upon 5. P of B is 1 by 5. P of A intersection B is question mark. Now I say that event A and B, what is given? Event A and B are independent. Therefore, possibility of A and B is equals to possibility of A into possibility of B is equals to possibility of A is 3 divided by 5 into possibility of B is 1 divided by 5. So this is 3 1 the 3 divided by 5 5 the 25. This is the required possibility. This is our first question. Simple question. Okay, now let us see the second question. Two cards are drawn at random and without replacement from a pack of 52 cards. Find the probability that both the cards are black. Okay, so here I will define two events. In the second problem, I will say let E is event that first card is black and F is event that second card is black. Now two cards are drawn. Question is two cards are drawn at random without replacement from a pack of 52 cards. Find the probability that both the cards are black. So here we have to find, probability of EF, or I will say that E intersection F. Now possibility of E intersection F is possibility of EF is possibility of E into possibility of F by E. This is our formula. Okay. Now possibility of E is possibility of E means the first card drawn is black. So out of 52 cards, there are 26 black cards. So it is 26 upon 52, which is 1 upon 2. And possibility of F when I know event E already happened. Means second card is black when I know that the first card is black. So as I know first card is black, then out of 26, one card already gone. So I have 25 remaining card from 51 cards. 25 black cards are remaining and total number of cards 51 are remaining. Okay, so F by E is 25 upon 51. Therefore, I have possibility of EF is equals to possibility of E is 1 by 2 into possibility of F by E is 25 upon 51. So 25 upon 51. So this gives us answer as 25 upon 102. Simple. I hope you are understanding what we are doing. Now third problem. A box of oranges is independent by examining inspected by examining 3 randomly selected oranges. Draw without replacement. If all the 3 oranges are good, the box is approved for sale, otherwise it is rejected. Find the probability that a box containing 15 oranges, out of which 12 are good and 3 are bad, will be approved for sale. So when you approve for sale, when all the 3 oranges are good. And how many good oranges are there? 12 good oranges are there. So let us write what is given and what we have to find. So here, third question, total number of oranges is equals to 15. Number of good oranges is equals to 12 and number of, what word they have used? Bad oranges. Okay. Number of bad oranges is equals to 3. Okay. Now, when all the 3 oranges are good, then I will select them for sale. So let us define 3 events. Event E I will define. Event that first orange is good. I will define F. Event that second orange is good, and I will define third event G as that the third orange is good. This is EFG. What I have to find? We have to find possibility of EFG. Means all the 3 oranges are good. This I have to find. So what formula I can use here? I can use the formula that probability of EFG is equals to probability of E, that is first orange is good, then possibility of F by E, that is probability of second orange is good, provided I know that the first orange is good, into possibility of G when I know that first orange and second orange are good. So this is how I can find probability of EFG. Now let us see individually. Possibility of E, that the first orange is good. Possibility of E is, now how many good oranges are there? Total 12 good oranges are there and total number of oranges is 15. So possibility of E is 12 divided by 15 is equals to 4 divided by 3 4s are 12 and 3 5s are 15. 4 upon 5. This is possibility of E. Possibility of F by E is possibility of F by E is that now second orange is good when I know that the first orange is good. So now I have total 11 good oranges because one good orange so we have already taken out by this F by E we know, and the remaining oranges is 14. So probability of F by E is 11 upon 14, and possibility of G, when I know that first and second orange are good, so remaining oranges, good oranges are 10 and total remaining oranges are 13. So therefore I will say that possibility of EFG, that is all three oranges are good, is possibility of E into possibility of F by E into possibility of G provided EF happened is equals to, now here possibility of E is 4 divided by 5 multiplied by 11 upon 14 multiplied by 10 upon 13. So here this 5 can cancel this 10, then this 2 ones are 2, 2 sevens are 14, and now nothing can be cancelled. So 11 into 4, 11 4s are 44 and 13 sevens are 91. So this is the possibility of EFG. Simple? Okay. Now let us see fourth question. A fair coin and an unbiased die are tossed. Let A be the event that head appears on the coin and B be the event that 3 on the die. Check whether A and B are independent event or not. So I have to check whether A and B are independent. Now I have tossed a fair coin and an unbiased dice. So in fourth problem, let us see what is given. So first I will write the sample space. Now sample space is head comma 1. I am tossing a coin and rolling a die. So head comma 2, head comma 3, H comma 4, H comma 5, H comma 6, then we have tail T comma 1, T comma 2, T comma 3, T comma 4, T comma 5 and T comma 6. So if I count how many elements are there, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. N of S is 12. Now event A. What we have defined event A? Let us check again. A be the event that head appears on the coin. So A, event that head appears on coin. So therefore I have A is equals to H1, H2, H3, H4, H5 and H6. So number of A is equals to 6. And what is your event B? Event B is 3 appears on a die. 3 appears on a die. So B will be H3 T3. So number of B will be 2. Now what is A intersection B? What is common to both A and B? So A intersection B is H3. Only H3 you can see that is common. So A intersection B is H3. So number of A intersection B is 1. Now I have to check whether A and B are independent. So when we can say that A and B are independent, when probability of A intersection B is equals to probability of A into probability of B. So here probability of A intersection B is equals to number of A intersection B divided by number of sample space is equals to 1 divided by number of sample space is 12. So it is 1 divided by 12. This is probability of A intersection B. Then probability of A is number of A divided by number of S is equals to number of A we got 6. So it is 6 upon 12, which is 1 upon 2. And probability of B, if I say, it is number of B divided by number of S is equals to 2 divided by 12 is equals to 1 divided by 6. So therefore possibility of A into possibility of B is equals to possibility of A is 1 divided by 2 into possibility of B is 1 divided by 6, which is 1 divided by 12. I will say this is equation 1. And possibility of A intersection B is 1 by 12. We already known this, so this is equation number 2. So from 1 and 2, you have possibility of A intersection B is equals to possibility of A into possibility of B is equals to so both are equal to what? 1 upon 12 we can write here. Therefore A and B are independent. Okay. You can mention the condition in the beginning also. Okay, so in the beginning you can say that event A and B are independent if possibility of A intersection B is equals to possibility of A into possibility of B. So somewhere I will say here after this line we can mention. So here in between we can say that key event A and B are independent if possibility of A intersection B is equals to PA into PB. So we mention this statement here and then find out. And then finally, when we get PA intersection B is equals to PA into PB, we will say that A and B are independent event. So fourth question done. Check whether A and B are independent. So yes, they are independent. Now fifth question is a die marked 1, 2, 3 in red and 4, 5, 6 in green is tossed. Let A be the event, the number is even, and B be the event, the number is red. Are A and B independent? So on die 1, 2, 3 they are in red color and 4, 5, 6 they are in green color. So there are 6 elementary outcomes. A be the event that number is even. So A is 2, 4, 6 and B is the event that number is red. So red is 1, 2, 3. I have to check whether A and B are independent. So again here what we can do in the problem number 5. In question number 5 we will write sample space. So sample space is 1, 2, 3, 4, 5, 6. So number of sample space, if you say n of s is 6. Event A is what event A we discussed? A is the event that number is even. So event A, the number is even. That means A is 2, 4, 6. Number of A is 3. And B is event that number is red in color. B is the event that number is red. So red are 1, 2, 3. Number is red in color. So your B is 1, 2, 3. So I have number of B as 3. Now A intersection B. Is there anything common? So 2 is common. So number of A intersection B is equals to 1. I will say that A and B are independent if probability of A intersection B is equals to probability of A into probability of B. So let us find probability of A intersection B first. Probability of A intersection B is number of A intersection B divided by number of sample space. Number of A intersection B is 1 and number of sample space is 6. So it is 1 by 6. Possibility, so we will consider this as equation 1. Now possibility of A into possibility of B is equals to number of A upon number of S multiplied by number of B upon number of S. So this is equals to number of A. Now what is number of A? A has got 3 elements, number of A is 3, so this is 3 upon 6 into B also has 3 elements, so 3 upon 6. So this is 1 by 2 into 1 by 2 is equals to 1 by 4. We consider this as equation 2 and this as 1. Now 1 and 2 if you see they are not equal. So I will say that from 1 and 2 probability of A intersection B, this is not equal to probability of A into probability of B. Therefore A and B are not independent. Simple. A and B are not independent events. Okay. So this is how we done the 5th question. Now let us solve one more question. So let E and F be the event. P of E is given, P of F is given, P of E intersection F is given. Are E and F independent? So very simple question. You can solve yourself. 6th problem. P of E and P of F is given, and P of E intersection F is also given. Again I have to check the value. What is the value? 3 by 5, 3 by 10 and 1 by 5. So here it is 3 divided by 5, here it is 3 divided by 10, and here it is 1 divided by 5. A intersection F is 1 divided by 5. Now let us check possibility of E into possibility. I will first write the statement that E and F are independent. If possibility of E intersection F is equals to possibility of E into possibility of F. Now possibility of E intersection F is 1 by 5. Let us see what is possibility of E into possibility of F. It is 3 upon 10 into 3 upon 5 into 3 upon 10. Okay. So this is 3 3 is 9 upon 10 5 is 50. And here E intersection F is 1 upon 5. So they are not equal. So therefore P of E intersection F is not equal to P of E into P of F. Therefore E and F are not independent. They are not independent events. Right? Shall we do one more problem? 7th problem. Given that event A and B are such that P of A is 1 by 2 and P of A union B is 3 by 2 and P of B is P, then find if they are mutually exclusive. Find P if they are mutually exclusive and independent. So P of A is 1 by 2, P of A union B is 3 by 5. 7th problem. P of A is equals to 1 divided by 2. P of A union B is equals to 3 by 5. P of B is equals to P. We have to find P if mutually exclusive. So here I have to find P. First case, when A and B are mutually exclusive, and second, when A and B are independent. Now first case I will discuss. When A and B are mutually exclusive, then nothing is common between A and B. So possibility of A intersection B is equals to 0. So when nothing is common, then possibility of A intersection B is 0. Now P of A union B is P of A plus P of B minus P of A intersection B. Therefore, P of A union B is given to me 3 by 5. So, therefore, I will say 3 divided by 5 is equals to possibility of A is 1 by 2 into no, it is plus possibility of B is P, and then here it is 0. So, therefore, P is equals to 3 divided by 5 minus 1 divided by 2 is equals to 6 minus 5 divided by 10 is equals to 1 divided by 10. So, the value of P is 1 by 10 when they are mutually exclusive. Second case, I have A and B are independent. So, when A and B are independent, then in that case P of A union B is equals to P of A plus P of B minus P of A intersection B. So, this is equals to P of A union B. Now, P of A union B, A and B are independent. Okay. So, what I can say that P of A intersection B is equals to P of A into P of B. Okay. So, P of A union B is PA plus PB minus PA intersection B. P of A union B is 3 divided by 5. So, write this as 3 divided by 5 is equals to P of A is 1 divided by 2. P of B is P minus P of A intersection B is P of A into P of B. So, here it is 1 divided by 2 plus P minus 1 divided by 2P. So, here it is 1 divided by 2 plus P minus 1 divided by 2P is P divided by 2 or 1 divided by 2P. So, therefore, I have P divided by 2 is equals to 3 divided by 5 minus 1 divided by 2 is equals to 6 minus 5 divided by 10 is equals to 1 divided by 10. So, therefore, P is equals to 2 into 1 divided by 10 is equals to 1 divided by 5. So, P is 1 divided by 5. So, when they are mutually exclusive, P of A in union B is 1 divided, value of P is 1 divided by 10, and when they are independent, value of P is 1 divided by 5. So, this is the possibility of event B in case when they are mutually exclusive and in case when they are independent. Okay. So, I think this have given you a fair good idea of mutually exclusive and independent event, what is multiplication theorem, right? There are few problems remaining that I think we can solve in our next class. So, thank you for being with me in this class. Thank you once again.